Hi guys, and welcome to today's video. Within this video, we're gonna see the importance of the vector table within the Cortex-M microprocessor and how it is used to properly boot the Cortex-M based platform, as well as jumping to the proper and correct interrupt service routine. And we'll finalize today's video by a demo running on STM32 microcontroller. The vector table by itself is just an array that consists of multiple entries, and each entry will hold and save the base address of the corresponding exception and interrupt handler, as you can see here. The structure of the vector table may differ from one CPU to another. For instance, on the Cortex-M 0+, we don't have the support of the memory managed fault, pass fault, and user fault. Hence, the corresponding entries within the vector table within an M0+ CPU are reserved. The system timer is optional within an M0+. Hence, if it is not available, then the corresponding entry within our vector table will be reserved. On M4 and M7, we have always the support of the memory managed fault, pass fault, user fault, and system timer. Hence, we will have always the corresponding entry for their handler available within our vector table. Now, beside holding the base addresses of the different exception and interrupt handler, the first two elements within our vector table are needed to boot our device properly, or to be more precise, to boot our Cortex-M microprocessor properly. The first element of our vector table consists of this initial stack pointer. During boot, the CPU will load the stack pointer initially from this value, or from this entry. The second element of our vector table consists of the address or the base address of our reset handler. Hence, during boot, the CPU will load the program counter with the value of our reset handler address. Hence, having our vector table properly set will allow booting our device properly, as well as jumping properly to the corresponding interrupt or exception handler. The vector table offset register is needed by the Cortex-M to store the base address of our vector table. This vector table offset register is 256 bytes aligned. Hence, our vector table must be 256 bytes aligned to be able to program it properly within our VTOR register. During boot, or during taking an exception or interrupt, the CPU will look into this register to extract the base address of our vector table to properly, first of all, load the stack pointer and reset handler address to our stack pointer register and program counter register, and secondly, to locate the correct and proper address for our interrupt and exception to be able to jump to it properly. Now, if we try to put both pieces together, we can see that the CPU, during an exception and interrupt, will just load the base address of our vector table out of the VTOR register. Then, we'll look into the exception and interrupt number to be able to locate the corresponding entry or index within our vector table. Then, we'll load the base address of the corresponding exception or interrupt handler out of the vector table to properly load this address into the program counter and start executing from there. So guys, as you can see, this is our Keil project. It is C-based one and has been compiled for this ARM Cortex-M microprocessor and has been loaded to our STM32 microcontroller. As you can see, this is the location of our vector table. So the first entry should match basically the initial stack pointer. This should be actually matching the reset handler base address, and each of those entries are matching basically the exception base address handlers as well as interrupts. To match basically this memory view with our program, we can check the disassembly. Now here, this is the address of our system timer handler. The system timer handler is occupying the entry number 15 from our vector table. Of course, if we exclude the stack pointer area. So this is the stack pointer, this is index 0, then this is reset handler, then this is NMI, so we need to calculate the proper, let's say, index. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So as you can see, this is the address of our system timer handler. or the address located in the entry number 15. And if we look into the assembly, we can see that this is the base address. So it's almost the same except the bit number 0, but this is logic because ARM try always to preserve the thumb encoding, hence it will set always the bit number 0 to 1. So if we set as well here the bit number 0, it will be 0x8000 to A5. And this is exactly matching the content of the entry number 15. So far so good. This should be actually matching, for instance, the reset ISR base address. So if we look into our assembly, we can see that this is the base address of our reset ISR, 0x800015C. And to preserve the thumb encoding, then we should set bit 0 to 1. So it will be 0x800015T. And this is exactly the entry number 1. So far so good. Now our vector table has been loaded into this memory area, and hence this base address must be programmed into our VTOR, or vector table offset register. Now this is the base address of our vector table offset register, 0xe000AD08. You can get this address from the system control block register descriptions within ARM, let's say, reference manual or website. As you can see, I have programmed already the VTOR with the correct base address of my vector table register, vector table area. As you can see, so 8 million went here. Now, in my program, I'm trying to trigger a static timer interrupt, as you can see, and then after the interrupt trigger it, I should jump here. Now let's check what will happen, and here we go. So as you can see, the CPU was able to locate the address for my SysTick handler out of the vector table from this entry number 15, because the SysTick timer has the number 15. So this, say, ISR field indicates the exception interrupt number that has been triggered, so it is 15. Then it will get the base address of my vector table out of this VTOR. Then based on those two inputs, the base address 8 million and the entry 15, it will be able to locate the correct base address of my SysTick handler, and hence will be able to jump to it properly.